Assalamu alaikum and good morning, everyone. So today is Monday, 21st February. We are going to continue with our topic 24, which is called Electrochemistry. In last lesson, we have looked at calculating the mass of the lead that was produced or deposited on the cathode. Okay, so electrolysis allows us to quantify either the solid being produced or the gas being produced during the electrolysis process. Okay, so there are a few things that you need to work out before you find out the mass of product being produced. First, you need to identify how many moles of electrons is required or released to form that particular product. In this case is lead. And then you have to associate that 2 moles of electrons, what is the charge that it carries? And we know that 1 mole of electron carries 1 Faraday of charge, which is 96,500 coulombs. So 2 moles of electrons would carry 193,000 coulombs of charge. So, and then we also want to know how much charge did we actually use in our electrolysis setup, okay? And we found out that we only use 1,800 coulomb, which is nowhere near the charge required to produce 1 mole of lead. Now, earlier on, we mentioned that the charge that you use in the electrolysis is directly proportional to the substance that is being produced during the setup. So that's why we can equate this ratio. Say if we had 193,000 coulombs of charge, we would have been able to produce 1 mole of lead of a product. However, we only use this much. So how much mole of lead would that be equivalent to? Okay, so we found that with 1,800 coulombs of charge, we could only form 9.33 times 10 to the power of minus 3 moles of lead. And the question is asking for the mass. The next step is to just convert using the mole expression, convert the number of moles of lead multiplied by the AR of lead to give you the mass of lead being produced during the process. Okay, we're going to do example 2.2 and the other questions 2.3, 2.4, and 2.5. I will let you try it yourself and I will give you the numerical answers later. Okay, calculate the volume of oxygen. So this time we are producing gas. That's why we quantify the volume. Produced at room temperature and pressure when a concentrated aqueous solution of sulfuric acid is electrolyzed. So if you remember, sulfuric acid would contain H plus, SO4 minus from the sulfuric acid itself. And because it is an aqueous solution, you would also have the H plus and OH minus. So usually the production of oxygen is when hydroxide ion is being selected for discharge at the anode. And again, if you don't remember, at anode, oxidation is happening. Okay, so that means you have to work out the half equation first. And if you don't remember, you can always go through your data booklet, find where O is because they are arranged alphabetically. And because we are looking at the reaction at the anode, therefore it would be an oxidation reaction. Oxidation reaction means it's the reverse equation. Therefore, you should be looking for hydroxide being on the right side to produce oxygen. So there are a few equation that has hydroxide ions on the right side, but we want to make sure that we're choosing the correct equation that produce oxygen gas. So that means it's this one. Okay, 4OH minus is being oxidized to oxygen plus 2H2O plus 4 electrons. Okay. Other information, your electrolysis setup is being run for 30 minutes using a current of 0.5 amperes. So find the number of coulombs to form 1 mole of oxygen. Okay, so here we are looking at how much charge do we need to produce 1 mole of oxygen. Okay, because it is an oxidation process, you would expect your electrons to be lost, which is on the right side. And that means to form 1 mole of oxygen gas, according to the balance equation, 4 moles of electrons is being released. Okay, so I will change that. 4 mole of electrons release, and the charge equivalent to 4 moles of electrons would mean 4 Faradays, which is 4 times 96,500 coulombs, and that is equivalent to 300. Okay, so that means to form 1 mole of oxygen, you need 386,000 coulombs in the electrolysis setup. Okay, so calculate the charge Q transferred during electrolysis. So now this one is the charge that was being moved around in our electrolysis setup, and to find that Q, we already know the formula. Q equals to IT, where I is the current in amperes, which is 0.50, and the time is in seconds, so you have to convert 30 minutes by 60 seconds. Okay, so that is a crucial step that you must always remember. Convert minute to seconds. Okay, so you should get 900 coulombs. Okay, so you want to know how much volume, but first we calculate how much mole of oxygen is produced if we had only 900 coulombs in our setup. So we would prepare the ratio table. So if you want to produce 1 mole of oxygen, you would require 386,000 coulombs. However, in our setup, we only have 900 coulombs. So how many moles of oxygen would that be? It should come out as 2.33 times 10 to the power of -3 mole. The question wants you to find the volume of gas, and remember that this is at room temperature and pressure. So if you want to convert the number of moles into volume of gas, you need to remember that in room temperature and pressure, 1 mole of gas is equivalent to 24 dm cubed. Okay, so to find the volume of O2, you have to take the number of moles of O2 times molar volume, which is 24 dm cube. Okay, so 2.33 times 10 to the power of minus 3 times 24 dm cube per mole. So that's dm cube mole minus 1. Okay, so the mole will cancel out. So your answer should come out as 0.0560. Okay, so your final answer should be that. Okay, I'll let you just copy this down quickly. Or you can pause this video to copy down the working. So the following questions, 2.3, 2.4, and 2.5, they are quite similar as long as you follow the steps. Okay, in the exam, you will not be given step 1, step 2, step 3, step 4. You would be asked, and the question would be as follows. Okay, there's no hint, there's no step. So try to practice with the next 3 questions using the steps that I have prepared for you based on example 2.1 and 2.2. You should be able to work out the answers. For 2.3, the answer is a mass of silver. Okay, so that means it's 5.44 grams. Okay, so please check that you can get the answer. Example 2.4, it's asking for the volume of hydrogen. So usually, if the question doesn't specify, you would just leave your answer in dm cube. So this one would be 0.157 dm cube. And lastly, example 2.5, where it is asking for the volume of oxygen. You should get 0.144 dm cube of oxygen. Okay. Right, we will move on to the next one, which is to calculate the Avogadro constant by an electrolytic method. So you can actually use electrolysis to find the value of Avogadro's constant. And of course, as you would expect, if we are to find out a constant number using experimental or from a practical, of course, the number would be slightly different, but it shouldn't be far off, okay? So for the learning objective, you are expected to describe the determination of a value of the Avogadro constant by an electrolytic method. So you are expected to be able to describe how you would carry out this experiment. Okay, so that means you can't just skip the steps. They might ask you things like, what are the required measurements needed to calculate the Avogadro's constant? Or they would say, draw a setup of electrolysis in order for you to calculate or work out the value of an Avogadro constant. Okay, so before we look at the setup, I would just like to show you this expression. Okay, L is equals to charge on 1 mole of electrons over the charge on 1 single electron. Okay, so I think it makes sense if you have the total charge for 1 mole, you divide it by the charge for a single electron unit, then that number would give you the number of electrons that make up the whole charge quantity. Okay, so this is actually, if you still remember, charge on 1 mole of electrons is 1 Faradays. Okay, and the charge on an electron is the symbol E, which is the value in your data booklet, it turns out to be 1.6 times 10 to the power of minus 19 coulomb. Now be careful, there is a negative charge. In calculation, you will leave out that negative charge because otherwise your answer would be a negative answer. Can you just imagine putting in charge on 1 mole of electrons as 96,500 and you divide by negative 1.6 times 10 to the power of minus 19, you would get a negative Avogadro's constant, which is not correct, okay? So this is in fact just a rearrangement of our F equals to LE expression that we have covered last lesson, okay? Okay, so your setup looks like a normal electrolysis setup where you would have a complete circuit. Okay, so first things first, you need to make sure that everything is connected. You've got your power supply, and then you've got your emitter. That's where you can read out your current in your electrolysis setup. The variable resistor, that's not for any recording of any quantity or quantifiable values. Copper anode, copper cathode, those are your electrodes, and then there's your electrolytes. Okay, so what happens is that first you would weigh your mass of copper anode and copper cathode initially before the reaction. Okay, because as you can see, copper here is a reactive electrode, so it will get involved in the equation. Now, what are the reactions that happens in this setup? Is the same way as you would work out the selective discharge. Okay, so copper sulfate contains Cu2 plus, SO4 2 minus. There's also H plus, there's also OH minus, and there is your copper electrode, which is reactive, and therefore it will be selected during discharge. So copper 2 plus would be picked up by the cathode. Okay, so that is where cathode is reduction. Okay, that's where reduction is happening. Copper 2 plus plus 2 electrode to form copper solid. And at the anode, instead of the hydroxide, which if we follow the easiness of oxidation, hydroxide should be selected. But in this case, because copper is reactive as an electrode, it will get oxidized. So copper solid will get oxidized into copper 2 plus and 2 electrons. Okay, so this is not a new equations for you. These are reactions that you know already. Okay, so you set up apparatus as shown. Again, as I said, the variable resistor is just to keep the current constant. It does not help you measure any quantity required for the calculation. Of course, if you know your current, which is I in ampere, you also need your time to find Q equals to IT. Time, you would use a stopwatch. Okay, so we're on the third step now. Close the switch and start the stopwatch. Pass a constant electric current for a measured length of time. So make sure that you record the time taken for you to let the current pass through along the electrolysis setup. When you're done, you stop the time, you open the switch, you record the time, and from there, since you know the ampere, you know the current from the emitter, and you know the time from your stopwatch, you can find Q is equals to IT. Okay. Right, step number 5. Okay, so as you can imagine, when you look at these two reactions here, at the anode, your copper solid, which is your electrode, will be releasing or will be producing copper 2 plus. Okay, so that means it loses electrons to release copper 2 plus, which means the mass of your anode would decrease because copper as an anode is being used up in this reaction. Okay, of course it doesn't go disappear, it wouldn't disappear, but you would see that the size of the electrode is thinning. Okay, and to quantify that, we would have to measure the initial mass and the mass of the electrodes after the reaction. Whereas for your cathode, you can see here, looking at the reaction, you're producing copper solid. So you would imagine there to be a layer of copper deposited around it. Okay, so again, you can also measure the mass of this cathode after the reaction. Okay, the idea is the amount of copper lost from anode is the same as the mass of copper being produced at the cathode, right? So moving on to step number 5. To remove the cathode and anode, wash and dry them with distilled water and then propanone. So basically you just want to clean, making sure that you do not have any impurities or anything sticking onto your electrodes. The mass of cathode should increase because we're producing solid layer around the cathode, whereas the mass of the anode should decrease, okay? But the amount is the same. If you decrease a certain amount of mass in the anode, you will increase the same amount of mass in the cathode. Okay, now, so we just have to choose one. Since they have the same mass, we just take either the anode or the cathode. But here it says that we will take the anode because it's easier and more accurate to measure the decrease in mass. The problem with increase in mass is that sometimes the copper layer doesn't stick well, especially when you put it out. Okay, as you pull it out, some of the copper solid may have dropped back into the solution, or even during washing, when you wash it with distilled water and propanone, some of the copper layer or the copper deposits around your cathode will be washed away. So then that decreases the accuracy of our mass of copper that is being produced around the cathode. Okay, so the easiest way is to just use the anode and we take the mass loss because mass loss will be equal to mass gain. Okay, so those are the procedures. So those are the steps, sorry. And we are now going to actually use the data that we found from the electrolysis experiment to find what L is. Okay, so here's the information. Sample result. In an experiment using the setup above, a current 0.2 amperes for 34 minutes. Okay, so from there you can already find Q equals to IT and the following experimental data. Calculate a value of Avogadro constant L. So just bear in mind, since you have current and time, you will need Q equals to IT, and you also need F is equals to LE. Rearrange them, you will get F over E. Okay, but except that this time your F is an experimental value, something that you can find from the experiment, but not E, right? So let's start with what can we start with? To find the mass of copper. Okay, since you've got Initial mass of anode to be 56.53. At the end of the reaction, the mass of anode is now 56.4. So you can see that there is a decrease. So mass of anode, mass of copper is equals to the mass loss, 56.53 minus 56.40, 0.13 grams. Bearing in mind, mass loss is equals to mass gain. So in the setup, we have produced 0.13 grams of copper. Okay, and then you can also find the Q equals to IT, where the current is 0.20 times converted to seconds. Okay, so just to highlight, that is the conversion to second. I'm not sure if I would have space here. Okay, next is times 34 times 60. 408. Okay, so that means if we use 408 coulombs to produce 0.13 grams, how much charge is required to produce 1 mole of copper? Okay. So I think I will need a blank page. Okay, so that means copper produced is 0.13 grams. I need to convert this to number of moles first, which is copper is the AR of copper. (63.5). Okay, so 63.5 mass over AR. Okay, so we are now sort of working in reverse this time. 0.00222 mole. Okay, so that means if we use berapa tadi our charge? If we use 408 coulombs, we get 0.00222 mole of copper. Okay, how much charge is required to produce 1 mole of copper? Okay, and that means we have to cross cancel 408 divided by 0.00222 moles of copper, which is 183,783 coulombs. Okay, so now is the charge. Now I want to look at the equation for the formation of copper, which I got it here just now. Okay, so copper 2 plus 2 electrons to form copper solid. So that's the reduction of copper 2 plus to form copper solid. Okay, so you can see that to form 1 mole of copper, we require 183,783 coulombs. Okay, so that means if you look at the equation, 2 moles of electrons is required to form 1 mole of copper. Okay, so if the charge that is required to form 1 mole of copper is 183,783 coulomb. Okay, what is the charge needed for 1 mole of electron? Right? So in order to produce 1 mole of copper, 2 electrons is needed. Okay, so that means this is equivalent to the charge of 2 electrons. I want the charge of 1 electron, which is what my symbol E is. Okay, the charge of 1 electron is equals to 183,783 divided by 2. Okay, and that is 183,783 divided by 2. Is this correct? I hope so. 91,891. Let me just double check again. 0.13 divided by 63.5. 0.00222. Okay. Yeah, that should be okay. So that means my F is a bit off. Okay. So if I want to find L, right? Oh, sorry. It's not a single electron. Is the charge of a 1 mole of electron, which is my F. What is the charge of 1 mole of electron? Okay, so that is my F. So L is equals to F over E. Okay, so my Faraday's based on this experiment is 91,891 coulombs over E, which is the charge of a single electron, which can be found here, is 1.6 times 10 to the power of minus 19. And that has a formula of coulombs. Remember here, okay? So the charge of one single electron is 1.6 times 10 to the power of minus 19 coulomb. The charge of 1 mole of Faraday's have been found based on my experimental value, okay, where forming 1 mole of copper would have required 2 moles of electrons, okay? And that means this number that we found here is associated with 2 moles of electrons. I will change the 2E. 2 mole of electron. So if we want to find the charge of 1 mole of electron, I have to divide it by 2. So that's why I found my Faraday's, which is the charge of 1 mole of electrons, to be 91,891 coulombs per mole. And if I calculate this, 91,891 divided by 1.6 times 10 to the power of minus 19 is equals to 5.74 times 10 to the power of 23 mole minus 1. And in our data booklet, our Avogadro's number is 6.02 times 10 to the power of 23 mole minus 1, okay, which is close, all right, a bit, it's not too bad because we're still in the factor of times 10 to the power of 23. Of course, it will not be exactly 6.02 because of many things. Actually, there are many human errors that can be associated during this experiment. For example, maybe when you stop the clock watch, okay, there will be reaction time, or during the washing or during the transferring of the electrodes. Yeah, so those are some of the factors that can affect the calculation of our Avogadro's number. Okay. Okay, I'll zoom this out for you, and then we will work out. We'll go through together the next example. Okay, so example 2.6. Yep, example 2.6. A student passed a constant electric current of 0.15 amps through a solution of silver nitrate using pure silver electrodes for 45 minutes. The mass of the anode decreased. Use this data to calculate the charge on a mole of electrons. Okay, so the charge on 1 mole of electron is our Faradays. We want to find Faradays. Okay, so you've got your I here, you've got your T, but bear in mind it's in minutes. The mass of anode. So our anode would be silver. Okay, so silver electrodes. Use this data to calculate the charge on 1 mole of electrons. Now, bear in mind the charge of 1 mole of electron is equivalent to Faradays. Okay, we want to find F here, charge on 1 mole of electrons. First, I would start with, actually, it doesn't matter. You can always start with Q equals to IT first, or you want to convert the mass of the silver into moles, because after all, we will be referring to the number of moles based on the half equation. Okay, so at anode, that means oxidation is happening. Oxidation. So you want to look at silver, which is Ag, which is the first one. Okay, so oxidation would be Ag being oxidized to Ag plus 1 electrons. So Ag will be oxidized to Ag plus 1 electron. So you can see here to deposit 1 mole of silver, okay, or to lose 1 mole of silver in this case, because we're talking about the loss of silver, you will release 1 mole of electrons. Okay, so this is already the hint. We want to find what is the charge when 1 mole of electrons is being released. That is equivalent to the formation of 1 mole of silver plus ions, or the decomposition of the silver solid. So Q equals to IT. So I is 0.15 amps times 45 times 60. Okay, where 60 is the conversion, minute to seconds. And that should come out as 405 coulombs. And when you use 405 coulombs, you would have used up 0.45 grams of silver. So we want to convert that into number of moles. Mass over AR. The AR of silver is, I believe, 108. Silver is 107.9. Okay, we'll use 107.9. So oh, they give you 108, but we'll use 108. 0.45 divided by 108, that comes out as 0.00416 mole. Okay, so what it means is that, just move it here, it means that if we used 405 coulombs, we would have decomposed 0.00416 mole of silver. Okay, so what is the charge released, because it's electrons given out, when we want to decompose 1 mole of silver? Okay, so you work out this ratio. It should work out as 405 divided by, so this is 97590 coulombs is the charge release charge for 1 mole of silver. Okay, but the question is asking for the charge on 1 mole of electrons, which is this number. Okay, since to use 1 mole of silver ion requires 1 mole of electrons, so the number is the same because of the 1-to-1 ratio. Okay, so that means the charge on 1 mole of electron is 97590 coulombs. And that is close to your Faraday's constant, which is 96,500. And if you take it to 3 decimal place here, it would be 97600 coulombs. Okay, so far you can see, based on example 2.5 and 2.6, in 2.5 you can work out the number or value of Avogadro's constant experimentally. In 2.6 you can work out the value of 1 Faraday's experimentally. It's just that sometimes they try to rephrase it in a different way, but it means the same thing. Okay, because 1 Faraday is equals to the charge on 1 mole of electrons. Okay, so I will leave this slide for you. The next part is the electrode potential, so I will not touch on that. I will start electrode potentials in the next lesson. So make sure you complete example 2.3, 2.4, and 2.5. Okay, and these are all on your notes, page 5. Okay, on page 5, I noticed that the numbering is repeated. There are 2 example 2.5. Okay, but the one that I want you to complete is on the one on page 5, and the one that we just did for L and F, where L is Avogadro's constant and F is Faraday's, is on page 6 and 7. Okay, so if you have any problem, please let me know. Otherwise, that is all for today. Okay, Assalamualaikum and thank you.